Welcome to CFD Engineering, I'm Rob, the lead engineer. In this video I'd like to show you the thermal simulation of a servomotor electronic controller device, how to set up boundary conditions, generate mesh, and analyze results in SC Tetra. The orange protective casing is made of 1mm gauge steel and has air vents on the top and the lower surfaces. In this already simplified model, the two green colored circuit boards, or PCBs for short, are fixed to an aluminum block which acts as a cooler and has mounting points to fix the controller to the mainframe of the machine it is originally built in. As you can see, not all components of the controller work at the same time, but these are the ones that add up the most severe load case. In an electronic thermal management simulation, the key design figure is the heat dissipated by the components, also known as thermal design power, or TDP. This heat has to be removed from the component to keep it below the maximum operating temperature to ensure long life and reliability. No worries if you as a thermal simulation guy don't know the name of all thingies on the PCB or how they work. I don't know all of them in this control unit either. All you need to be aware of are the TDPs and what material each component is made of. For the moment, that's enough. Let's prepare the model. The blue box is the air surrounding the controller, and it's an important part of the design because the controller unit works in a quite small compartment without any vents. To make the orange casing suitable for a nice SC Tetra feature, I'm turning the solid parts within SC Tetra preprocessor into a surface model by deleting the internal faces. It would take loads of tiny mesh elements to build the 1mm thick metal, so instead I'm using its outer surface and apply a software feature later on. When it's done, I'm telling SCT to recognize all solid volumes. This will give us the list of all components with their names, which comes handy in the simulation for assigning TDPs. This is the point when SC Tetra cleans CAD geometry. It automatically fills closed cavities and removes overlaps. Final step of preparation is called tessellation. This means that the parasolid model is converted into one that uses triangle surfaces only. I'm giving it a name, save it and load it for further processing. At this point comes a little challenge. As you can see, SCT has recognized 81 closed volumes, and this is already a simplified geometry. Additionally, most of the volume region names are part codes the designer used, so they don't really tell me anything about which part is which. It's a challenge because each part has to be given one of the 9 material properties this unit uses. I double-click on the volume region name so SCT marks the parts. Next, I make SCT display the volume number of the marked region in the message window at the bottom. For this plug, it's 81. So I go and find 81 in region registration on the right and assign material number 2, which is going to be steel later on. The next region name has 8 microchips in it, so I get their volume number listed, find them in region registration and assign mat number 6, which represents silicon. This way I can assign the right material number to all 81 parts in 10 minutes. I will get back to you when I'm done. As the mat number assignment goes on, it gets easier to find the region number in the registration window, so it's not that bad. If you have a quicker way of doing it in SC Tetra, just let me know. Let's move on to materials. Out of the 9 different materials, first is convective air to simulate natural convection. Solid parts have steel, aluminum, ferrite, polystyrene materials with constant thermal property values. But silicon, which is the most interesting one for electronics applications, has temperature varying specific heat and conductivity. Apart from these, I will use copper as heat bridge between the aluminum block and parts attached to it, and finally I set printed circuit board materials that have anisotropic conductivity depending on layer orientation. Now that I have assigned materials to part groups, the next step is to sort out those individual parts that have heat energy release. As I mentioned earlier, not all the parts work all the time, so I have to find and name those that are on in this load case. I'm using the same workflow as with the material number assignment. I'm marking the part group by clicking on its name, I'm asking for the volume number, and in volume registration I give the volume a name that I finally understand, based on TDP figure and location in the unit. It takes roughly 10 minutes to find all the parts and properly name them, so I get back to you when I'm done. This is the last silicon chip I'm naming on the upper side of the small board. Its TDP is 0.25 watts. Right, I'm done with naming volume regions, but I also need some surfaces of the air compartment to set heat transfer conditions later on. I'm registering top and side surfaces as a group, the bottom surface separately, and finally the outer surface of the aluminum cooling block. Let's move on to analysis settings and boundary conditions. I'm using laminar flow and switching temperature simulation on. I'm also turning the heat conduction panel feature on, which will allow me to use the surface model of the steel casing. Next, I'm setting 500 iterations and turning gravity on. Now the heat conduction panel. This is the cool feature I mentioned earlier that saves me a lot of mesh elements. To do this, I'm choosing casing model surface region, giving it 1 mm thickness, and I'm choosing steel as material. Initial condition is 25 degrees C temperature for all materials. Default boundary conditions set up the simulation in general. It saves me some time and I can further refine boundary conditions in the next step, which deals with surfaces. I'm setting wall heat transfer coefficient to those surfaces of the closed compartment which are in touch with the environment. The ones that are surrounded by air will get 5 watts per square meter Kelvin at 25 degrees outside temperature, while the bottom that touches another metallic surface will get 10 watts per square meter Kelvin. Moving on to heat sources, I'm first setting condition at the outside surface of the aluminum cooling block. It is mounted to the steel frame of the machine, so I'm setting 50 watts per square meter Kelvin at 25 degrees C, which is lower than the expected component temperature, so heat will be removed. After all this, I'm setting TDPs to volume parts. Their names are telling me what TDP I should use, so this goes quite fast. Let's jump to solver settings. As the simulation domain is completely closed, I have to show the solver a pressure reference point. For this, I'm defining one in the top corner and setting 0 Pascal static pressure to it. In output control, I'm clicking all the volumes I have set TDPs to, so that I can have their temperature without any additional manual work, as SCT writes these out in a text file. Out of curiosity, I also want to have average air velocity in the closed compartment, so I register the volume and ask SCT to write this out into the text file too. What left is to set frequency of automatic saving of results and restart files, and I'm saving all the simulation settings as a text file, which I'm going to use to start a solver. Next, I'd like to show you how automatic mesh element size definition goes. I'm generating 5 million elements as a starting point using 2.5 mm base mesh element size. Depending on the model dimensions, SCT increases or reduces base size to fit into the 5 million limit. I prefer having a uniform element size in parts, and as you can see, the 8 chips have 2 different element size levels. I make SCT show the larger elements, and I'm manually decreasing their size by 1 level. I check all parts to make sure the ones that are important and have TDP assigned to them will get a uniform mesh size. Due to manual refinement, the system increased the number of mesh elements by 10% to 5.5 million. However, this is not the final number, as there will be boundary layers and depending on geometry, some cubes will be split into tetrahedrons. To run mesh generation, I need to refer to the tessellated model, the mesh size file and the settings file. At this point, I tell SCT to keep as many cubes as possible, and I also set the number and thickness of the boundary layers. When it is ready, the mesh contains 11 million elements. On a cross-section you can see that SCT has kept cubes where it could, and 3 boundary layers surround all solid parts including the casing surface. After all this preparation work, I can run SC Tetra Solver now. All I have to do is to drag and drop the settings file I saved previously. Depending on the computer, it would take some time to finish 500 iterations, but I already have the results ready, so let's jump ahead. As streamlines show, air is leaving the control unit through the upper vents, so there must be air inflow through the lower vents. The top of the scale is unfortunately at 90 degrees C, so it's getting a bit warm in there. Let's hide the casing. Well, those 2 chips on the tiny vertical board are getting warmer than healthy, and small chips on the lower side of the smaller board must feel uncomfortable too at 85 plus degrees C. Why is it so? The problem is that air warms up to 65 degrees C by the time it gets to the tiny vertical PCB, which means no cold, fresh air gets to the hottest area of the control unit. When I change the lower end of the temperature scale to 70, it's clear that chips on the tiny PCB are between 89 and 90 degrees C, and smaller chips at the bottom are at around 85 degrees C. Results text file shows the exact number. Small chips are between 84 and 87 degrees C. Bigger ones on the vertical PCB are between 89.4 and 90.4 degrees C. The ideal would be 60. If we don't want to burn all these components to the ashes, we have to change the ventilation system, and I guess some heat sinks would also be beneficial. In the next episode I will show you what I would do to improve the situation. I hope you enjoyed this video. Please consider sharing and subscribing. Thanks for watching, see you next time.